Okay, we're still working our way here through Chapter 10, Section 10.1. We just came off of looking at how to run a confidence interval for estimating the difference between two population proportions, and now we're going to shift to looking at how to conduct a significance test for the difference between two population proportions. Okay, now I think the important thing to note is how these tests are labeled on your calculator. On the calculator, it's actually called a shorthand 2-prop Z test. Okay, that's short for 2 proportion Z test. We know the two references, we're taking 2 samples, one from each population. Proportion, that's what we're comparing. Z, we use Z scores anytime we're talking about proportions. The T-scores are used for means, and test for significance test rather than confidence interval. Okay, now the good news is these conditions are exactly the same as they were for the previous confidence intervals that we discussed. There is an alternate name for this. Rather than a 2 proportion Z test, you could also call it a 2-sample Z test. They have to say what it's for proportions. Okay, it could also be named this way if you were listing the name of it on a free response question. The reason I tend to gravitate more to calling it a 2 proportion Z test is simply because that is how it is labeled on the calculator screen. So if you were going to use the calculator feature for this, it's kind of nice to just sort of use the same labeling as how you would expect to see it in the menu on the calculator. Okay. Now, we did discuss anytime you're doing 2 samples, there was this extra condition, making sure that the 2 samples are independent, but we were often kind of lumping together in the same sentence the statement that the 2 samples were both random and independent. Of course, you can see we have the 10% condition that needs to be shown for both samples, and that large counts condition, which also needs to be shown for both samples. Okay, what you see in these boxes here below, now remember, we're discussing now significance tests. Significance tests have these null hypotheses that we can write. Okay, and the null hypotheses, as you recall from before, are always statements of equality. So you can say this one of 2 ways. You can either say that the 2 proportions are equal to each other, or this is essentially saying the same thing here. If you were to bring this P2 over to the left side and subtract it, you would be saying that the difference between those 2 population proportions is 0. Okay, so in other words, this is always indicating that there is no difference between your 2 population proportions. And that is always the assumption that we begin with, and then we see if the evidence points towards these alternative hypotheses, which would indicate a difference between the 2 population proportions, in which case we would then choose to reject our null hypothesis. So the alternative options are one of these 3, and you can see there are 2 different ways of writing this, that the first population proportion is greater than that of the second, or if you were to bring that second over, you can see that the difference is greater than 0, that it's less than, or that it is not equal to it, but doesn't necessarily give one specific direction. Okay, now this next part can get a little bit confusing. Okay, now remember, when we do these sig tests, we are assuming that our null hypothesis is true. That is always how you start a significance test. We are assuming that the null hypothesis is true. Now I want you to look at what the null hypothesis would be. We would be assuming that the 2 population proportions are actually the same. Okay, so if we're assuming that these 2 proportions are the same, then technically our best estimate for what the overall population proportion would be from each of the populations would be to pull together the 2 samples, almost viewing it as a single sample, and using that combined proportion as both our best guess for P1 as well as for P2. We call this a pooled proportion or a combined proportion, okay? Now you would be doing this with your samples, like the p hat sub 1 and p hat sub 2. So when you combine them together, we combine it together and we use this notation p hat sub c, representing we've combined together, we've pulled together both of the samples into a single sample. Now again, why would we want to do that? Well, if we are assuming that the two population proportions are both the same, then there's no harm in pulling them together into one large sample. It just provides more data, especially if the sample sizes were small, and it would give what the combined sample proportion would be as our estimate for both p hat sub 1 as well as p hat sub 2. So here's how this would work. Your denominator would be a combination of adding together both of the sample sizes, which we know those don't have to be the same, and then your numerator would be you combining together and summing what the number of successes were in both of the samples. Okay. When we do this, and I'm just going to kind of label here that this represents the probability of a success for each population. Okay, so it's going to be exactly the same for what we would end up using here for each sample's probability of a success. Right, so the standard error for the difference between two population proportion samples is given by this formula right here. Okay, now I will tell you on the formula sheet, I believe that this is the generic version for how to get your test statistic. That would be your z-score if we were doing proportions, except I think that it replaces, instead of standard deviation, it calls this the standard error of the statistic. Okay. Now we'll talk through what should be plugged into each of these three pieces, but right now I'm focusing on the denominator. That is the standard error of the statistic, which would be calculated by this formula right here. Now you'll notice instead of p hat sub 1s in these two spots and p hat sub 2s, we're using the exact same proportion in those areas because we have pulled together, and so we're using that same probability or proportion of successes for each of the two populations. So here's an example just to try to drive this home a little bit here. Let's say that our null hypothesis was saying that the proportion of students who are taking statistics, and in a statistics, like let's say AP statistics, the proportion of students who take AP statistics who get a 5 on the AP stats test is equal to, I'm going to change this sub here, I'm going to change this to CA, okay, is equal to the proportion of students who are taking AP calculus who get a 5. Okay, now remember, the null hypothesis says that those two proportions would be equal. So then we go to a school and we survey 12 AP Stats students, and we 4 AP Stats students, and we discover of those 4 that 2 of them ended up getting a 5 on their AP Stats test. So that sample proportion is a half, or 2 out of 4 got a 5. Okay, then we also sample from a school how 8 calculus students, AP calculus students, and we discover that of those 8, 1 of them scored a 5 on their AP calculus test. So our sample proportion for that is 1/8. Now you can see we're getting different sample proportions, but our null hypothesis is assuming that the true proportion of students who get 5s, whether they're in AP Stats or whether they're in AP Calculus, is actually the same. So when we go to calculate our test statistic, for our standard error here, what we want to use is we want to use a combined proportion. We want to pull together this as one big sample. So I'm going to combine the 4 students and the 8 students and say technically I sampled 12 students. The total number of successes, total number of 5s, whether they were stats or calculus, is 3. And so I'm going to use 3/12 in each of these spots here for my combined proportion here. And the reason it's okay that I do that is because the null hypothesis is assuming that those two proportions are equal to each other, at least amongst the populations, even though it didn't come out that way in the samples. Okay. Now you can see this is filled in a little bit more clearer for our test statistic is the z-score. The statistic that we're estimating here is this difference between the two sample proportions. It's definitely worth noting that our parameter, that always comes from our null hypothesis. And so the difference between these two proportions, if we're saying they're equal to each other, would be 0. So this is always a 0 when I'm calculating the test statistic. And then you can see that the standard error of the statistic would be given by this formula right there that's circled. Okay, so I'm just going to make a little note down here that this is always a 0. Okay, that's always 0 here. Okay, so let's move to the next page here. Got a little bit of a summary here at the top, and then we'll see if we can try to do this with an example or two. Okay, one thing that I want to make sure that you're okay with is we should only be pulling samples together for 2 proportion sig tests. Okay, you would never do this if this was for not comparing 2 proportions, but rather 2 sample means. This is only for 2 proportion sig tests. And we get that again by summing the successes in the numerator over the sum of the sample sizes in the denominator. And you'll note then we end up using that same pooled sample proportion in those 4 areas. Okay, we also said that this spot right here, this is always a 0, okay, for no difference between the proportions. So in this example, we're going to be comparing the proportion of successes from 2 populations using a 2-sample z-test. I prefer to call this a 2-prop or 2-proportion z-test. Okay, it says the hypotheses and samples for each population are, and then they give us, here is our null hypothesis, that there is no difference between the 2 population proportions, and then our alternative is that yes, indeed, there is a difference between them. Okay, you can see we drew out a sample from the first population. Our sample size was 25. 16 represents the number of successes out of those 25. Gives us a sample proportion for the first population of 64%. When we did that from the second population, our sample size was 72. You can see that we got 57 successes out of those 72 for a sample proportion from our second population of 0.792. Now it is asking us here to find the combined or pooled sample proportion by hand. So what we would be doing for this is we would, in the denominator, combine together the 2 sample sizes. In the numerator, combine together the 2 number of successes for a combined or pooled sample proportion of 0.7526. That is the number that we would use in each of these 4 areas here for our standard error of our test statistic. Now again, for these significance tests, when we're comparing a difference between 2 proportions, the 2 samples are pulled together as one large sample because we can get a more precise estimate when we are using more data. And the reason we're allowed to combine those is since the null hypothesis is assuming that the proportion of successes from each population is the same. Okay, so then it asks us down here for this problem to go ahead and calculate the test statistic. That is the z-score. That would be this formula that you're seeing up here in this yellow box. That's what we're going to calculate, the test statistic. Okay, and so in this spot here, we would be subtracting our 2 sample proportions. Okay, that is not combined. In fact, you keep that separate. The 0.64 minus the 0.92. We said this is always 0 because our null hypothesis is implying or assuming that there is no difference. We're only combining those and doing our pooled proportion here for the standard error of our test statistic. So I'm using 0.7526 times the probability of a failure, which is 1 minus that. I'm doing that same thing in both of these numerators, but my denominator is each separate sample size. You can see that right here, okay? So we're only pooling things together to create this p hat sub c value. Okay, these denominators are each their separate sample sizes. Okay, if we were to type that in, we would get our z-score value of negative 1.517. Okay, now remember, our alternative hypothesis on this was a statement of does not equal to. That means this is a two-tailed test. So that means this would bound that, and over here I would get the positive version of that. I would be looking for that shaded area. Now, we're going to do this on the calculator, and in all honesty, if you're doing any free response questions like this, you should be using the calculator feature for this. So on the calculator, what we would end up doing is you would press that stat button, you would bump to the right to the test menu, you would see that it is option number 6, and it is called to-prop z-test, as we said before. Okay, when you select to-prop z-test, it's going to ask you for these inputs. Okay, you want to make sure that you're always reporting whatever inputs it is asking you to write down, and that you always identify the name of the test. Okay, x sub 1 is number of successes from sample 1, and n sub 1 is the sample size. We'll write that same thing down for the second sample, and then you want to make sure that you're choosing the correct direction for the alternative hypothesis. On the screen, if you go into that option 6, you'll see that you definitely want to pick the does not equal to, because that's what the alternative was. Okay, and this will then spit out for you what that test statistic is. I think that it shows you negative 1.514. When we did it by hand, it was negative 1.517. Okay, it also does give you the p-value for you to make your decision and compare that with the alpha level. But we're going to look at one example here from start to finish, and we'll be able to do it on the calculator as well here. So let's look at this as our last example here in this video. It says researchers designed a survey to compare the proportions of children who come to school without eating breakfast in 2 low-income elementary schools. An SRS of 80 students from school 1 found that 19 had not eaten breakfast. Okay, so in this chart that you see down here, it's identifying school number 1. This 80 is the sample size from school number 1. The 19 is what we're looking for, so we're calling that the number of successes. Remember, a success doesn't have to mean something positive. So obviously, children coming to school who have not eaten breakfast is not something that's positive, but that's the thing that we're trying to measure. So that is the number of successes, 19 out of 80. Okay, we read on. It says, at school 2, a simple random sample of 150 students included 26 who had not eaten breakfast. So our sample size from school 2 is 150. The number of successes, those who did not eat breakfast, were 26. More than 1,500 students attend each school. Now, this is given to us probably, so when we get to the 10% condition, we know that we're staying underneath that population size. When you see the phrase, does the data give convincing evidence of a difference in the population proportion, that indicates they are wanting us to run a significance test. Okay, we're looking for, is there evidence that there is a difference in these 2 population proportions? Wants us to carry out a significance test using an alpha level of 0.05. Okay, you can see I have the Phantoms acronym down the side. We want to start with P, identifying the parameters. We're going to use P1. This is the true population proportion of, make sure we're using context here, of students from school 1 who did not eat breakfast. Okay, we're going to say the same thing for P sub 2, only we're going to be talking about school 2. So the true population proportion of students from school 2 who did not eat breakfast. Okay, the H is where we list what our hypotheses are, and we list the alpha level. Okay, now remember, our null hypothesis is always a statement of equality. So we are going to assume that the true proportion of students who come to school not eating breakfast is actually the same for both of these schools. The alternative, this is where we want to come back up here and we want to look, it's saying, is there a difference? It doesn't indicate anywhere that I read that one school is expected to have a larger proportion who are not eating breakfast than another. So we're just going to use a does not equal to sign. This will be a two-tailed significance test. And we want to state what the alpha level is, 0.05. Okay. All right. Now, our A for assumptions, which is our conditions here. Okay, the first condition, we want to say that each sample, notice it had said up in the problem SRS, that's short for simple random sample. So I'm going to say each sample was taken randomly and independently. Okay, we want to make sure we get that independently in. And we're just going to assume that if it doesn't mention it, and it seems realistic here, but we do need to state that we are assuming that in order to move forward with our significance test. Okay, the 10% condition, need to do this for both. Okay, that 10 times the sample size of 80, as well as 10 times the sample size of 150, that these are both less than or equal to 1,500, which is what the number of students were they told us up here attended each school. Okay, so I can check off that. We're good there. Now our third condition is the normality condition. This is what we know as the large counts condition. Okay, now the large counts condition is where we are supposed to list the number of successes and failures for each of these 4 schools. Now, I want to point something out here. Normally, we say n times p, n times 1 minus p. We need to do that for each of these schools here. Now, I want to identify what p hat sub 1 is. Okay, that is 19 out of 80, and p hat sub 2 would be 26 out of 150. Okay, but let's look at this a little bit closer here. If I take the number in the sample from school 1 times the probability of a success, or the proportion of those who are not eating breakfast, look at what I end up getting. I end up getting 19. So what I have in this chart right here, 19 is the number of expected successes from school 1. 61 is what I would get for the number of expected failures. Same thing here for school 2. These are my counts already. Now I need to list them, but I can just kind of list that these numbers, success, failure, these are all greater than or equal to 10. Okay, rather than writing out n times p, n times 1 minus p for each of these, and I'm just going to end up getting these 4 numbers that are already there in the chart. Okay, so I can check off the normality condition. All right, the N is for naming the test. This is a 2 proportion Z test. Okay, now I would encourage you on these problems, because it is just so involved to pull together the 2 samples, to use the formula and be doing this by hand. I would encourage you not to do this by hand. Now, you'll notice in this box, I went ahead and put all of that information there for you. Okay, it has this added extra thing too, especially because our alternative hypothesis was a does not equal to. It was two-tailed, that if you do it by hand, the p-value you get has to be multiplied by 2 to account for both of those tails. Whereas if you use the calculator feature, it already has it doubled when it reports the p-value. Okay, so I'm going to have you go to the calculator. I'm going to have you press the black stat key. I want you to bump over to the test menu, and I'd like you to choose option number 6, called the 2-Prop-Z test. Now here's what you're going to see on your screen. And I'm just going to flip to the next page here so that you can see this illustrated on these calculator snapshots that I have here for you. It's going to ask you to input the number of successes, sample size for population 1 or sample 1, same thing with sample 2. Also note that you should be highlighting the does not equal to, because that was the direction for our alternative hypothesis, and we would come down and select the calculate menu. Okay, all these things that I highlighted in orange and yellow though, that's what you have to report as this step here before you say what the test statistic, your z-score, is. So you need to report what you were inputting in the calculator, which is nothing new. We've always had to do this even when we did normal CDF. We've had to label what our calculator inputs were. Okay. When we do this, you can see again on this next page what's reported for you is there is our z-score, 1.17. So I'm just going to jostle back here and go ahead and write that down, 1.17. The O is us obtaining the p-value. Okay, this is our p-value. That's the shaded area. Okay, this is our shaded area here. That is what we have right here, 0.2427. That's what I'm going to report as my p-value here for the O step, obtaining the p-value. Okay, now I'm going to make my decision. Okay, and this is where I compare. I'm going to say, since p of 0.2427 is greater than my alpha level of 0.05, we fail to reject the null hypothesis. Okay, if we're failing to reject the null hypothesis, that's when we are going to make a statement saying that we do not have convincing evidence that, now, what you're stating next is whether you have evidence that you should look at what the alternative hypothesis is and say that in context. Remember, our alternative hypothesis was a statement here that there is a difference between these two proportions. Okay, if they're not equal, that we're saying that there is a difference. So there is not convincing evidence that there is a difference in the two population proportions, here's my context, of students arriving without eating breakfast at the two schools. Okay. Again, I highly encourage you to just go ahead and use that calculator feature. Just make sure you're reporting the things that you're needing to input. Okay. Here